What's up, what's up, what's up mga Chimek? It's your boy Sir Jello once again for another chemistry adventure. So last time we have discussed about Dalton's law of partial pressure. So if you've missed it, you can check my videos, no? The Dalton's law of partial pressure lecture and the practice problem that comes after. So for this session, my dear Kachimek, we are going to talk about the Graham's law of effusion. So first, no, I'd like to congratulate you on behalf of for surviving and conquering the first room. No, sabi niya, congratulations, you were able to open and survive the first challenge. However, after opening that particular door, you find yourself in a room with, again, of course, you're still with Kachimik Irma, Kachimik Levs, Kachimik Marian, and Kachimik Jello. And inside the door, in a room, it's an empty room with only a stopwatch or a timer and a video, a TV to give you the instruction. So the game master, so is that the name of that thing, of that doll? So I don't know. Basta the game master, has given his instruction. He said, there's a hole that you must find in this room, and eventually, accidentally, someone found that hole. No, it's you because you're the good Kachimek. Pushed accidentally the center of one wall, and it turns out to be a hole, a passageway. And yan, the video further says that you need to cross that hole in order to survive, in order to leave the room, because in 1 minute that room will be burned, it will become an inferno, you'll be burned alive if you cannot leave the room in 60 seconds. So since you were so good in your mathematics while the video is playing, and you are blessed with estimations, you estimated that Kachimik Irma and Kachimik Lev, since they are both thin and light, they can cross the hole consuming 10 seconds. While Kachimik Marian and Kachimik Jello, since they are both heavy, they can consume 15 seconds each. Now the question now, how many seconds do you have to cross the room? Alright, you may now pause the video and compute. Alright, if you got 10 seconds, you're actually correct. What did you do? You compute the speed or the rate of both of the 4 Kachimiks that are in that particular room. So Kachimik Lives plus Kachimik Irma can consume 20 seconds. Jello and Marian can consume 30 seconds. So 20 plus 30, that will give you 50 seconds, and you have 10 seconds to escape the room. So if you got 10 seconds, very good, you got it correctly. So ladies and gentlemen, this is just a warm exercise for our in preparation for our topic for today. So for today, these is our objectives, Hopefully at the end of the session, we are able to describe what Graham's law of effusion is. We are going to try to relate the rate of gas of effusion with the molar masses of the elements or compounds. And then we'll try to solve some practice problems involving Graham's law of effusion. So are you ready, mga Kachimek? Alright, let's go, let's go! Alright, now before we proceed any further, as I've mentioned a while ago, this is our last discussion on the gases, specifically the behavior of gases. I'd like to reiterate to you the importance of kinetic molecular theory, or how do gases behave. Because you'll be needing this in your college or in your future career, the foundation of how gases behave. Well, in summary, according to kinetic molecular theory, law of repetition says if you repeat a topic or an idea over and over again, it becomes the student gains mastery over it. So hopefully hindi kayo maumay kahit inuulit-ulit natin. A gas consists of many particles, either atom or molecules. We don't really care. What we care about is that we know that they are not stationary. They are constantly moving in random motion, and there is no attraction between them. So we again assume that there are no chemical reaction happening inside a chamber, inside a particular container. The amount of space, of course, occupied by a gas is much bigger, or yeah, the gas part, the space occupied by the gas is much bigger as compared to the gas themselves, meaning very spacious ang container nila or ang area where they move randomly. And then we also need to understand that the average kinetic energy of a gas particle is proportional to the temperature in Kelvin. So what do we mean by this? No, if you can remember in Gen Chem 1 when we were discussing gases becoming ions, no, I told you that a gas stove or a lighter or any kind of flame, no, or any source of flame is actually burning you not because of the flame, but because, or not because of the hotness of that flame, because temperature is not really the hotness or coldness of an object, but rather it's the average kinetic temperature, no? Si kinetic dito, tas tatawa ka. the average kinetic temperature. But you are being hurt because the flame or the gas has a very high temperature, meaning since it's the average kinetic energy, it's moving very fast. No, it has a lot of energy, and that is a sudden transfer of energy. That's why your tissues, no, the atoms in your finger are being torn apart. No, it's not actually burning. No, it's actually like slicing, no, in a microscopic world. No? Hopefully you can remember that particular discussion, and if not, hopefully you realize something, that that's the temperature, or that temperature is just actually the average kinetic energy of any object or anything. It's not the hotness or coldness, because there's no such thing. And finally, the collision between the gases are elastic. So I've reminded you of this one during the discussion on Dalton's law of partial pressure. So hopefully you bear this in mind. And if these things are too technical, just remember that gases behave just like human. No, what do I mean by that? Diba? We are moving in a random motion. Diba? Human. Some are going north, some are west, east, and south. No, we are in constant motion. No? We don't like to be stationary. And when it's cold, no, we tend to hug someone, diba? During maybe if you watch movies, history movies, no, tribes gathering together to when it's too cold, no, to preserve the warmth, no. So even in modern times, when we are cold, we tend to be with people, no? Diba? During Christmas, that's why it's time, or winter, no, it's time for celebration because it's too cold, no. We like gathering. Maybe that's the reason why Christmas and many gatherings are during winters, no? And then, yan, kung wala kang kayakap, diba? Mag-ano ka, magkumot, or you hug yourself, no? In lonely, especially sa mga walang kadate ngayong Valentine's Day, sad life, no? Pero at least hindi sad boy. Alright, no? The cold air tends to move a little, no? Or very slow. They tends to gather or clump together as compared when it's hot. No, human, when it's hot, no, I know that that person is hot, pero yan, when it's hot, we tend to move around, no? Diba? We tend to travel from places to places, and we don't like to stick with each other, diba? Ang init, tapos magyayakapan pa. Kaya meron tayong joke na, ala, ano na yan, naglalandian ka, alas 12 tapat. Diba? Because it's too hot. No, we'd love to do it when it's cold, diba? So human and gases are actually very, very similar, diba? When it's hot, we tend to move around, diba? So that we can create more, or we can get more air, no? We can be refreshed, no? So ganyan din si hot air. The more we increase the temperature, the more it moves faster, diba? That's why we don't throw aerosol cans in flame, because if the gases are still inside, no, and they increase in temperature, the kinetic energy of these gases will also increase, creating explosion, no, and several other experiences, or yan, in our daily life. And most importantly, you know, one of the significant behavior of gases is just like when human are trapped in a place like this, now, Viva la Virgen, no? I don't know if you have experienced this. No, I often, I'm a devotee of the Peña Francia, Our Lady of Peña Francia, and I've been witnessing Traslacion and Fluvial Festival for several years now. And actually, I tried, no, at least once to reach that particular place, no. However, wala pa ako sa katiting or sa kalingkingan, if you may call it. I'm very far. Natrap na ako sa mga tao. And the tendency of a human and even a gas is to travel from high concentration to low concentration, meaning from matao, you need a space. Now, if you can find a spot where there are no people, you'll go there. No, similar to the gases. And when we talk about the gases, no, we call this transfer from high concentration to low concentration, no, diffusion. All right? So take note of the term. It's diffusion. 'Di ba? Si Sangoku tapos si Vegeta, diffusion. Char lang. It's diffusion or diffusing or scattering of molecules from high concentration to low concentration. To formally define it, no, it's the process whereby gaseous atoms and molecules are transformed from regions of relatively high concentration to regions of relatively low concentration. Diba? And it's not only true to gases or to humans. It's true to liquid. Liquid tends to go from places where they are highly concentrated to a more spacious area, and that's how we maintain the blood in our body, and other biological process. There's a lot of benefits because of this diffusion, a natural tendency of a gas to proceed from a concentrated area to a low concentrated area. Now, the problem here in gases are we want to determine the speed of the gases. Now, how long will it take for me to smell the adobo that I am cooking or the tinola that I am cooking? Or maybe you have wondered, bakit kaya laging adobo lang naaamoy ko sa second floor? Bakit hindi ko naaamoy yung nilulutong carbonara? No? Bakit eto lang lagi yung naaamoy ko, yung cheese lang? Bakit hindi ko yung barbecue lang? Bakit hindi ko naamoy agad yung cheese? Things like that. And if you've wondered about things like that and you want an answer, so ladies and gentlemen, this video is very appropriate to you. No? In early 1800s, people have already computed. It was an easy job to compute the speed of a moving object, but it was very difficult to compute the speed of gas. Diba? When we compute of the speed, or particularly the velocity of a moving person or a moving vehicle, we just simply use the formula distance over time. Meaning, to get the velocity, we need to take the distance covered and divide it to the time used in covering that particular distance, and we get the velocity. However, gases are very different. Many have attempted to try to measure the speed or velocity of gases. However, they failed. Why is that? It's because gases travels randomly in different motion. It's unpredictable. Remember, kinetic molecular theory says that they are moving in random motion, either individually or either collectively or as a group. And there are times that magbabanggaan sila, di ba? So, it's very difficult until very brave and very intelligent, very creative scientist discovered something that could aid, cannot really solve the diffusion rate of gases, but he presented something else. Now, before I tell you what it is, let me introduce to you, ladies and gentlemen, Thomas Graham, FRS, FRSE, DCL. Diba? Ang daming title, no? Parang si Dalton, FRS lang. Si FRS is, as I mentioned, it's fellowship from Royal Society. It's an award given by London, to distinguish effort in contributing scientific knowledge. Si FRSE naman, it is given by, same lang siya sa FRS, Fellowship of Royal Society. However, this is given by Edinburgh, I forgot the country. Edinburgh ata. Yan. Yeah, I'm not really good in geography, but somewhere near London. No? And then DCL, no, this is Doctor in Civil Rights. So, madami siyang title. Si Thomas Graham. He was known in pioneering work in dialysis, but more importantly, gases, no, that we are going to tackle today. So, similar to the challenge given to you by So, he realized that since we cannot measure the movement or the velocity of gases since they are moving in random motion, in random direction, what if we force them to enter a single direction or to travel in a single direction? And how do we do it? No, we do it best. Char. We do it by creating a hole from one container to another container. And with this, no, we can maximize the kinetic molecular theory. First theory, they are moving in random motion, and second, they tend to move from high places or high area with high concentration to area that are low with low concentration. And this is the low concentration is a vacuum because we are dealing with gas, no? Dapat wala itong laman. As in, it's a vacuum chamber. And with this, no, we cannot measure the distance traveled by a specific gas, no, as it enters the pinhole. He call it a porous hole or a tiny orifice, if you may call it, or you can simply call it a hole. No, we cannot measure the distance traveled, but rather we can use something else. And what is that? Very good. No, we can count how many moles, how many or the number of gases that can enter from this place going to this place. No? How long would it take for one gas, one molecule of gas, or for all the molecule of gas to enter or to transfer from this area to this area? And this is what he called, no, since he cannot call this diffusion because it's not scattered, it's from one direction to, it's a single direction only, no, it has only one way to go, this hole. He call it, anong sunod sa D? E. Effusion. Di ba? Talino ni Sir Jello. Joke lang. He call it effusion. No? And since it's not talking about the distance traveled, but rather how many, he cannot call it the velocity of effusion or the velocity of gas, but rather he call it the rate of effusion. Alright. And by definition, no, rate of effusion is determined by the number of molecules that diffuse, no, or effuse through the hole in a unit of time. So don't get confused. The effusion is just a term for a diffusion passing through a single hole. So say for instance, let us put it in mathematical example. We have 1, 2, 3, 4, 5, 6. Let's say we have 6 moles. 6 mole of what kind of gas? Okay, with 6 mole of gas X, no, para wala pang specific. And after 5 seconds, and 1 mole of gas X has already transferred from this area to this area. Alright, now, what is the rate of effusion of gas X? Now, how are we going to solve the rate of effusion of gas X? Now, Graham presented this very simple formula, which is very related to velocity. He said that in order to get the rate of effusion for this one, we will simply use the rate of effusion. How many moles of gas? We can use N over period of time. So since I got 1 mole of X over 5 seconds, therefore the rate of effusion of this particular gas, now this X gas, is 1 mole per 5 1 mole per every 5 seconds, or I can convert this one to 0.2 moles, 2 moles, yeah, bear with me, per second. Alright, did you get it? So 1 over 5, that would be 0.2, one significant figure per second. So the rate of effusion is 0.2 seconds. So what's the important of this one? Diba? We can see, we can actually compute how long will it take for item number 1 in your Google Classroom that I'll be uploading through Google Form. Write your answer for this question. How long would it take for all of the gases, or ito na lang, for all of the 5 gases to transfer from this area to this area, We are looking for the time. So again, for item number 1, how long would it take for these gases to transfer from this area, from this low concentrated area? Alright, that's item number 1.